I'm Bindusree, working as an assistant professor in the Department of Electronics and Communication Engineering at Institute of Aeronautical Engineering. Today, the topic is binary arithmetics and octal arithmetics and the BCD arithmetics. Okay, so in the binary arithmetic is a part of all the digital computers, many other digital systems. So first one is the binary addition. In the arithmetic, including the addition, subtraction, multiplication and division. Okay, in the binary addition, so here we are taking the two input values A and B. Two input values A and B. So two combinations, we are taking the two combinations AB 2 power 2 equal to 4. So total combinations are the 4. So in the binary addition we are using the plus. Okay. So in the A and B bits, so here we are adding the two bits. Here we are taking the two input values AB and 4 combinations is there. So A equal to 0 and B equal to 0. So in the 4 cases, so in the first case 0 plus 0. 0 plus 0. The sum is 0, carry is also 0. Next, here the A equal to 0 and B equal to 1. A equal to 0 and B equal to 1. So 0 plus 1. The sum result is the 1, carry is the 0. Next case, A equal to 1, B equal to 0. 1 plus 0. The sum equal to 1, carry equal to 0. Next, A equal to 1 and the B equal to 1. So 1 plus 1. So here the sum is 0, carry is 1. Sum is 0, carry equal to 1. So here we are taking the only two input bits, 4 combinations is there. So in the case of A equal to 1, B equal to 1, carry equal to 1, sum is 0. So here we are adding the, if we are taking the more number of the 2 bits, means if we are taking the A, B, C bits are there, both the 3 input bits are the 1, 1, 1. So what we are getting? For example, 1 plus 1 plus 1. So the carry is 1 and the sum also 1. This is the binary addition. So let us take the one example. 1 0 1 1 plus 1 1 0 1. This is the example of the binary addition. Now I want to add the 2 bits. So 1 0 1 1 and 1 1 0. Okay. So now I want to add the 2 bits. A equal to 1 and so this is the input for the A. This is the value for the B. Okay. So 1 plus 1. So here the carry is 1 and the sum is 0. Next one. 1 plus 1. 1 plus 1. Carry is 1. Sum is 0. So again 1 plus 1. 1 0. So the sum is 0. 0 plus 0 is 0. Carry is 1. Okay. So next one is 1 plus 0 is 1. 1 plus 1 is 1. 0. Carry is 1. Sum is 0. Okay. Now I want to add the 3 ones. 1 plus 1, 1 0. So here the carry is 1 and the sum is 0. So again we are having the one more bit is there. So that will be added in the sum. 0 plus 1, 1. Carry is 1. So the resultant value is the 1 1 0 0 0. So here the carry is 1. The remaining bits are the sum resultant value. This is the binary addition. So here we are taking the 1 0 1 1 and 1 1 0 1. So these inputs are equal to the, so now we are now we want to convert this binary values into the decimal form. So 2 power 0, 2 power 1, 2 power 2, 2 power 3. 8 plus 2, 10 plus 1, 11. So first bit is the 11 plus 1101. 2 power 0, 2 power 1, 2 power 2, 2 power 3. Okay, 8 plus 4, 12 plus 13. So 11 plus 13, 26. So this is the 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. 13 plus 4, 24. 16, 2 power 4, 16 plus 3, 18. So 24. So both the answers are same. This is the binary addition. Next one is the binary subtraction. So in the binary subtraction also, here we are taking the 2 input bits. If you are taking the 2 input bits, 4 combinations are there. So that outputs are the subtract and borrow. The input bits are the A and B. So possible conditions are the 1 to 4. Okay. So 0 minus 0, 0 and borrow also 0. Okay. 1 minus 0. 1 minus 0. The subtract is 1, borrow is 0. Okay. So here we no need to take the borrow values. Next one. 1 minus 1. 0. Borrow is 0. Next. 0 minus 1. So this means, so subtracting the lower value to the higher value. So now we are taking the borrow of the previous next bit. Okay. So that's what here the borrow is 1. So in the binary subtraction, we are having the values only zeros and ones. But here we are taking the borrow is 1, 0. So now I want to subtract with the 0, 1. So now here we are taking the borrow of the 1, 0. Okay. So 1, 0 minus 1 is the 1. So borrow is the, okay. So this is the binary subtraction. So based on this, so we'll see the one example of this one. Same examples. So 13 minus the 11 plus 13 is the 24. So let us take the 13 minus 11. 13 minus 11, 4. So normal decimal subtraction. 13 minus 4 is the 11. So here we are taking the 1, 1, 0, 1 minus 1, 0, 1, 1. Okay. So 2 power 0, 2 power 1, 2 power 2, 2 power 3. 8 plus 4, 12 plus 13. Okay. So now we are subtracting the two values. 1 minus 1, 0. 1 minus 1, 0. So here the 0 minus 1. 0 minus 1. So this is not possible. So that's what we are taking the borrow of this previous bit. So that is the 1, 0. 1, 0. So here 1, 0 minus 1. Let us take the one more example of this binary subtraction. So the values are the 13 minus 11. So 3 minus 1 is the 2. Okay. So this is the decimal subtraction. So we'll see the binary subtraction. So 13 equivalent binary value is the 1, 1, 0, 1. So 11 equivalent binary value is the 1, 0, 1, 1. Okay. So 1 minus 1, 0. So 0 minus 1. So it is not possible. So we should take the borrow of the previous bit. So that is the 1, 0. 1, 0. So 1, 0 minus 1. So that value is the 1. So here we are taking the borrow of this bit. So the value is the 0 only. So 0 minus 0 is 0. Next one, 1 minus 1 is the 0. So 0, 0, 1, 0. 0, 0, 1, 0. So this is the equivalent of the 2. This is the normal binary subtraction. So here we are taking the improving the more number of, here we are taking the more number of the bits. So if that bits, we are taking the one binary subtraction. So in that subtraction, we are taking the borrow. So compared to the decimal subtraction, binary subtraction is the somewhat complexity. Why? Because so here we are taking the some previous bits, we are taking the borrow, again we are taking the borrow of this previous bits. So that is a somewhat complexity. We want to overcome this one. We are going to the complements of this one. So that complements are the r's complement and r minus 1's complement. So what is the r? So that number system base or radix value is the r. So in the binary arithmetics, we are taking the r's complement means in the binary base value is the 2, 2's complement and 1's complement. So we want to overcome this one, we are going to the 1's and 2's complement. Even we are going to the 1's complement and 2's complement, we want to get the same result of that normal subtraction, then we are going to the complements. Okay. So first we'll discuss this one, 1's complement of these values. 1's complement of these values. So let us take the values 13 minus 11. 13 minus 11. So in the 1's complement addition, 1's complement addition. So whatever the subtrahend value is there, we are applying the 1's complement of that value. So next one, add that 1's complement of that resultant value and the original value. If the carry is present, that carry is added into the LSB bit, we are getting the result. If the carry is not present, so that is again we are apply the 1's complement of that resultant value. So apply the 1's complement. So in this, for this 11, we are apply the 1's complement. So in the 1's complement, 1's will change it to this zeros and zeros will change it to this 1's. So 0, 0, 1, 0. Okay. So this is the 1's complement of 11 equal to 0, 0, 1, 0. Okay. So this 13 equivalent value is the 1, 1, 0, 1 plus 1's complement of this 11. So this 0, 0, 1, 0. Now we are adding these 2 bits. So addition is easy. So 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. Okay. So here we are taking the value is 11 is equal to this. So here we are taking the 11 minus 13. Why? Because so this value is the 13 value. So here we are apply the 1's complement of this 13 equal to 0, 0, 1, 0. So 0, 0, 1, 0 and add the 1, 0, 1, 1. So here we are getting the value is 1 plus 0 is 1. 1 plus 1 is 1, 0, 1, 1. Okay. So here we are not having the any carry. Here we are not having the any carry. So again we are apply the 1's complement of this resultant value. So the sign is the negative. Apply the 1's complement 0, 0, 1, 0. So here we are getting the minus 2. Minus 2. Okay. So but here we are taking the decimal value is the 13 minus 11. So we'll see the example of this one. Same example we'll take this in this 1's complement also. Okay. So first one is the this value is the 13 equivalent value. Okay. So next one is the we'll take this 1's complement of the 11. So 11 equivalent value is the 1, 0, 1, 1. Apply the 1's complement 0, 1, 0, 0. 0, 1, 0, 0. So the 13 equivalent value is the 1, 1, 0, 1. So apply the 1's complement of this one is the 0, 1, 0, 0. Now add these 2 bits. 1 plus 0, 1. 0 plus 0, 0. 1 plus 1, 1, 0. 1 plus 1, 1, 0. So here the carry is present. That carry is added into the LSB bit. So 1 plus 1, 1, 0, 0 plus 1, 1, 0, 0, 1, 0. So this is the equal of this 2. So sign is plus 2. So here we are subtracting the decimal value. 13 minus 11 is the 2. So in the binary subtraction, we are getting the value is the 2. So if we are applying the ones complement of that values, again we are getting the 2. So the answers are same. So now I want to apply the 2's complement. Same bits, we are applying the 2's complement. Okay, so for this 11, we are applying the 2's complement. Okay, so first apply the 1's complement of this one, 0, 1, 0, 0. Okay, so add the 1 into the LSB bit, 1, 0, 1, 0. 0, 1, 0. Okay, so in this 2's complement, first take the 11, 13, 1, 1, 0, 1. Apply the 2's complement of this 11, 0, 1, 0, 1. Now add this 2 bits. 1 plus 1, 1, 0, 1, 1 plus 1, 1, 0. Again 1 plus 1 is 1, 0. So in the 2's complement, carry is present. Ignore that carry. So 0, 0, 1, 0 is 2 plus 2. So if we are following the any different ways, we are getting the same result only. 13 minus 11, 2. So this is the decimal subtraction. Coming to the binary subtraction 2. So we want to overcome this complexity. We are going to the 1's complement and 2's complement. So in this 1's complement and 2's complement also we are getting the same result. Okay, so that's what we are going to the 1's complement of this digital electronics. For the instead of the binary subtraction, we are using the complement of this R's and R minus 1's complement. This is the binary subtraction. So next one is the binary multiplication. So this binary multiplication is the same as the decimal multiplication. So here also zeros and ones are needed. Okay, so same. So if we are multiplying with the zeros, we are getting the same resultant value. Okay, so means taking the 2 inputs AB 0, 0, 0, 1, 1, 0 and 1, 1. The result is 0, 0, 0 into 0, 0. So multiply with the any bit with the 0, we are getting the same 0 value. So 1 into 0 is 0, 1 into 1 is 1. Okay, so the example of this one is 101 into 110. 101 into 110. So first multiply with the 0. So 101 into 0. So 1, 0 into 0, 0 and 0. Next, we are taking the multiply with the 101 into next bit 1. 1, 0, 1. Next multiply with the 1. 1, 0, 1. 0. 0 plus 1 is 1. 0 plus 0, 0. 0 plus 1 is 1. 1 plus 0 is 1. 1. So the result is the 1, 1, 1, 1, 0. Okay. So this is the binary multiplication. Next one is the binary division. So it is the same as the decimal division only. So here we are follow the long division procedure. Okay. So for example, in this binary multiplication, we are converting these values into the decimal. So 5 into 6 value is the 30. So here 2 power 0, 2 power 1, 2 power 2, 2 power 3 and 2 power 4. Okay, 16 plus 8 plus 4 plus 1. Okay, 10, 14 plus 16, 30. Okay, so either the decimal multiplication and binary multiplication, we are getting the same resultant value. Okay, so coming to this binary division, same as the decimal division. So we are taking the example, we are taking the 2 bits 3 and 6. 3 and 6. 2 is 6, the value is 0. So now I want to convert these decimal values into the binary form. So 0, 1, 1, 1, 1, 0. So this is equal to this 3. This is equal to this 6. Okay. So 0, 1, 1 into 1, 1, 0. So either it will be multiply with the 1 and 0. So first multiply with the 1. So 0, 1, 1 into 1. 0, 1, 1. So here we are subtracting these two values. 0 minus 1. Not possible. So that's what here we are taking the borrow of this one. So 1 only. Okay. So again here we are having the 0 only. 0 minus 1 is not possible. Again we are taking the borrow from the previous value. So 1 only. Here the 0 is there. Okay. So again it will be multiplied with the 1, 0, 1, 1. So in this binary division also we are taking the binary subtraction. Here we are using the binary subtraction. Okay. So that's what this is the complexity of this one. Binary division also complexity. So similarly, we are having the octal arithmetic is there. Octal arithmetic is there. So in this octal arithmetic also, so we are having the 6 complement is there. In the octal arithmetic also, r's complement is there, r minus 1's complement is there. So what is the octal arithmetic? What is the octal arithmetic? So in this octal arithmetic also, so let us let's see the addition and subtraction. Addition and subtraction. So first we will discuss about the octal addition. Octal addition. So in this octal values we are having the only zeros and 0 to 7 values only. In the octal base value is the 8. So coming to this octal addition, so here we are taking the 3 bits. So n equal to 3 bits, we are getting the 8 combinations are there. 8 combinations are there. So from the 0 to 7, we are having the same values. When the resultant value is getting the 8, so the value is equal to this 10. Value is taking the 8 equal to 10. So why? Because, so this is the decimal value. Now I want to convert this octal. So what is the procedure? So divide with the 8. 8 ones are 8, 1, 0. If you are taking the 9 value, so this is the decimal equivalent values. This is the octal equivalent values. So the decimal value is the 9. Now I want to convert the decimal value to this octal. So that is the 1, 1. Next one, 1, 0, 1, 2, 1, 1, 1, 3, 1, 2, 1, 4, 1, 3, 1, 5, 1, 4, 1, 6, 1, 5, 1, 7, 1, 8, 1, 6, 2, 0. So why we are getting the 2, 0? So in the octal values we are having the 1 to 7 1, 0 to 7 only. So when we are reaching the 2, 0 means 8 16 times 8 2 0 0. So 2 0. 15 times 7 1. So whenever we are adding the two octal values greater than the 7 means we are getting this resultant values. Okay, so let us take the one example of this octal arithmetic, means octal addition. So in this first one is 4, 6 and 3, 2. 4, 6 and 3, 2. So 6 plus 2. 6 plus 2 is the 8. So in this octal arithmetic, we are not having the 8 value. So that is the equal to the 1, 0. So 1, 0. 4 plus 3 is the 7. 7 plus 1 is 8. So this 8 is not also possible. So taking the 1, 0, 0. So this is the, if we are assuming these two values are the octal values, then this is the resultant value. So for example, these two are the decimal values. That decimal values are converted into the octal. Decimal values are equal to this octal. So then we are getting the resultant value. So we'll see that one. So first one is, for example, these two are the decimal values. In this normal addition, 78 only. Okay. So now I want to convert these decimal values into the octal. So 46 is there. So 46, the value is the 5, 6. So octal value of this 46 is the 5, 6. Next one, 32, 40. Okay, 6 is there. So here the 6. 5 plus 4, 9. So 9 is not possible. So that's what 116. Okay. So here the carry is present. So this is the, whenever we are converting these values into these octal values, we are getting the resultant is 116. So this is the octal value. So now I want to convert this value into this decimal. Then we are getting the resultant value. For suppose, so these two values are converted into this octal values. Similarly, this will be converted into this octal value. 72, 6 times 8 ones are 8. So the value is the 116 only. Same, we are getting the same values. Okay. So these two are the decimal values. So now we are adding these two decimal values are 78. So now I want to take the octal addition. So this 46 will be converted into the octal form. We are getting the 56. Similarly, this 32 is converted into this one, 40. We are getting the 116. So this is the normal octal addition value. Okay. So similarly, same values we are taking the octal subtraction. This is the octal addition. Okay. So next one is the octal subtraction. So we'll see this octal addition, octal subtraction, and the r's complement and r minus 1's complement. Okay. So in this octal subtraction, octal subtraction. Okay. So the decimal values are the 6 and 4. 6 and 4. So either these two values are the less than the 7 number. So these two are considering the octal values also. So in this octal subtraction, 6 minus 4 is the 2. Now we'll see the 8's complement and 8 minus 1's complement. So r's complement and r minus 1's complement. So this is the octal complements are there. So now we are getting the 8's complement. So what is that one? So subtracting each and every value with the 8, then we are getting the resultant value. That is the 8's complement. So coming to this 8 minus 1's complement. So subtracting with the 7. So adding the 1, we are getting the 8's complement. Okay. So this one octal subtraction, r's complement. Next one is the r minus 1's complement. First, I want to take this r's complement. So this is the 8's complement. 8 minus 1's complement. So this is the 7's complement. Okay. So now we want to take the any value. Now we want to find the 7's complement. Subtracting with the 7. Some 6, 2 is there. So subtracting with the 7. 7 minus 2, 5. 7 minus 6 is the 1. This is the 7's complement. So now I want to get the 8's complement. So subtracting with the 7, we are getting the 1, 5. So adding 1 into the LSB bit, 1, 6. So this is the 8's complement. Okay. So apply the 8's and 7 complements of this decimal octal values. First one. So coming to the 7's complement. So in this one, we are taking the bits are the 6 and 4. So first apply the 7's complement of this one. So 7 minus 4, 3. 3. So this is the first step. Coming to the second step, 6 plus 3. 9 is there. 6 plus 3, 9 is there. Okay. So this 9. So in this 9 is not there in this octal value. So that's what we are taking the 1, 1. 1, 1. So if the carry is present, that carry is added into this LSB bit, we are getting the 2. Okay. So first step, apply the 7's complement of this subtrahend, adding the original bit and plus the 7's complement of that bit. We are getting the 9 value. Converted that 9 to the octal value 1, 1. So in this one, presenting the carry, that carry is added into the LS bit, we are getting this one. So this is the 7's complement. So coming to this 8's complement. So this answer is same, this answer is same. So coming to this 8's complement. Coming to this 8's complement. So in this 8's complement, so again, we are having the 6 minus 4, 2 is there. So again, we are apply the 8's complement of this one. So 7 minus 4, 3. 3 plus 1 is the 4. So this is the 8's complement of 4. Okay, this is the first step. So second step, add to this 6 plus 4. That value is 10. So in the octal value, 10 is not there. 10 is not there. So this value is equal to this 8. Equal to this octal value is 8. So this is not there. So ignore this carry. So first we are apply the 8's complement of this one. This 4. 8 complements of this 4. 4 is there. So 7 minus 4, 3. So 3 plus 1 is 4. Okay, 8's complement of this 4 is the 4. So now we are adding the 6 plus 4. The value is 10. The value is 10. So 10 is not including in this bit, in this octal value. So again it will be converted into this. So apply the 8's complement of the 4. So 7 minus 4 equal to 3. 3 plus 1 is 4. Okay, now adding the 6 plus 4. 6 plus 4. So this is the 8's complement of 4. Okay, so now add the 6 plus 4, 10. So this is the octal value. So in this octal number system, we are not having the 1, 0. So that's what we are converting this 1, 0 to this 1. So we are getting the 8 1 are 8, 2. So this 10 equivalent value is the 2 only. So in the 8's complement, carry is present. So ignore that carry. Ignore the carry. So this is the resultant value. So that is the plus 2. So here we are applying the octal subtraction, and the r's complement and r minus 1's complement. So we are getting the same resultant value. So addition is very easy compared to the subtraction. So by using the complements, we are indirectly adding these 2 bits. So that's what we are going to use the octal addition. So octal complements, r's complement and r minus 1's complement. Similarly, in this hexadecimal arithmetic also, same procedure. Hexadecimal addition is there and the hexadecimal subtraction. Again apply the 15th and 16th complement of that values. So here we'll see this hexadecimal arithmetic. Hexadecimal arithmetic. In this hexadecimal arithmetic, so addition and subtraction is there. So this is the normal addition. Zero 2 and 0 5. This is the decimal addition. Same numbers are using in this hexadecimal also. So from the 0 to 9, we are having the same values in the hexadecimal also. So this is the normal addition. Okay, and the hexadecimal addition also same. So if you are taking the subtraction is there. So that is the 5 minus 2 is 7. 5 minus 2 is the 7. So in the subtraction also we are having the same numbers. 5 minus 2 is 7. So same values are presenting in the ones and r's and r minus 1's complement. So what is the r's complement? In the hexadecimal base value is the 16. So by using the 15's complement, so apply the subtrahend into this 2. So 15 minus 2, so 13. 15 minus 2 is the 13. So that is the first step. Second one is 5 plus 13. 18 is there. So 18 is not including in this hexadecimal value. So that's what we are converted into this hexadecimal value. So that is the 12. That is the 12. So carry is presenting. So 2 plus 1 is the 3 only. Sorry, here the 5 minus 2 is the 3. We are getting this one. So again we are getting the same resultant value. So we are applying the r minus 1's complement. So coming to this r's complement. So that is the 16's complement. Okay. So the subtrahend value is the 2. So first apply the 15's complement of that one. 15 minus 2 is 13. So now I want to the 16's complement. Add the 1 into the LSB bit. That is the 14. So this is the first step. In the second step, so 5 plus 14. 5 plus 14 is the 19. Okay. So 19 is not including in this hexadecimal value. So this equivalent value is the 13 only. 13 only. So in the 16's complement, so if the carry is present, ignore that carry. So this is the original value. So in the hexadecimal normal subtraction, apply the 15's complement of that value and the 16's complement of that value. We are getting the same resultant value. Okay. So in this today's session, we'll discuss the binary arithmetic, octal and the hexadecimal arithmetics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.